You walk out to your driveway on a freezing winter morning. The ambient temperature is hovering somewhere around 20 degrees Fahrenheit, and you turn the key in the ignition. Instead of that familiar, immediate roar of the engine coming to life, the starter just cranks and cranks heavily. Maybe the engine stumbles violently for a split second, shakes the entire car, and then completely dies. You are sitting there in the cold, gripping the steering wheel in a complete panic, immediately assuming that your expensive fuel pump has catastrophically failed, or your timing chain just snapped. You are already calculating how many thousands of dollars this is going to cost you at the dealership. But before you call a tow truck and surrender your wallet to a mechanic, you need to understand exactly what your engine control module is attempting to do during that initial cold start. Because the actual culprit might be a microscopic piece of wire that you can fix yourself in your own garage for less than $10. When you cold start an engine, the computer relies entirely on a sequence of sensor readings to calculate the precise fuel pulse width needed to ignite a freezing cylinder. Cold air is incredibly dense, meaning it is packed with oxygen, and the freezing cold metal of the engine block instantly absorbs the heat from any combustion that tries to happen. To counter this extreme environment, the computer commands a very rich fuel mixture. But if it gets the wrong data regarding how much air is actually entering the intake manifold, it will either starve the engine of fuel or completely flood the spark plugs with raw liquid gasoline, leaving you stranded in your driveway. The component responsible for this vital measurement is the mass airflow sensor, and it is arguably the most critical yet completely neglected piece of hardware in your entire fuel injection system. Before we dive into exactly how this sensor fails and the delicate process required to save it, take a quick second to hit that subscribe button so you never miss out on these hardcore, real-world garage diagnostics. Now, the mass airflow sensor does not measure air volume. It measures actual air mass using an incredibly fascinating piece of thermal physics. Inside that plastic housing in your air intake tubing, there is a tiny, fragile platinum wire that is roughly the thickness of a human hair. The engine computer constantly sends a precise electrical current through this wire to heat it up and maintain it at a very specific, constant temperature. As you step on the gas pedal and outside air rushes past this heated wire, the air cools it down. The computer instantly measures exactly how much extra electrical current is required to keep that wire hot against the rushing wind, and within milliseconds, it translates that electrical data into the precise mass of oxygen entering the cylinders. The nightmare begins when microscopic dust particles, vaporized oil from cheap reusable air filters, or environmental smog make their way past the airbox and bake onto that superheated platinum wire. This layer of baked-on grime acts as a thermal blanket. The wire stays artificially hot because the dirt insulates it from the incoming cool air. The computer is suddenly blind. It thinks you are barely touching the throttle when you are actually accelerating hard, so it cuts the fuel supply. The car hesitates, stumbles, and falls flat on its face. The fix is incredibly simple but requires absolute precision. You must remove the sensor housing and use a dedicated mass airflow sensor cleaner spray to melt the grime away. You can never, under any circumstances, physically touch that platinum wire with your fingers, a cotton swab, or a shop rag. The oils from your skin or the slightest physical pressure will permanently snap the element, turning a simple 5-minute cleaning job into a $250 parts replacement. While we are talking about unmetered air messing up your fuel mixture, we have to look at the dark, oily underworld of the engine block itself, specifically the positive crankcase ventilation system. Every single time a spark plug fires and an explosion pushes a piston down, a small amount of highly pressurized toxic combustion gas blows past the piston rings and gets trapped down inside the engine oil pan. We call this blow-by. If these gases are trapped down there, the internal pressure of the engine block rapidly skyrockets. This immense pressure will violently force motor oil out of your front crank seal, your rear main seal, and your valve cover gaskets, covering your driveway in expensive synthetic oil. To prevent this, engineers use a PCV valve to route those toxic, oily vapors out of the crankcase and dump them directly back into the intake manifold so they can be burned off in the combustion chamber. It is a brilliant system until that cheap plastic valve inevitably fails. If the internal spring wears out and the PCV valve gets stuck wide open, it essentially creates a massive, uncontrolled vacuum leak. The engine is now sucking in a huge volume of air that completely bypassed the mass airflow sensor we just talked about. The computer goes crazy trying to figure out why the engine is running so lean, causing a violently shaking idle, random misfires, and a massive drop in your MPG. On the other hand, if the valve gets completely clogged with oil sludge and sticks closed, the pressure has nowhere to go. Suddenly, your engine starts burning oil. You see thick blue smoke coming out of the tailpipe when you accelerate, and your expensive gaskets start weeping fluid. This tiny piece of plastic costs about $15 and should be replaced every 40,000 miles as basic preventative maintenance. Yet almost nobody even knows it exists until their engine starts leaking from every single seam. A rough idle and a stalling engine does not always mean you have an air or fuel problem, and this is where modern automotive engineering tricks a lot of amateur mechanics into wasting thousands of dollars on parts they do not absolutely need. If you are driving a modern vehicle, like a Ford F-150 with the 5 V8, or almost any BMW produced in the last 20 years, your engine utilizes variable valve timing to maximize both horsepower and fuel efficiency. These systems use highly pressurized engine oil to actively rotate the camshafts while you are driving down the highway. This incredible mechanical feat is controlled by variable valve timing solenoids, which are electronic valves bolted right into the cylinder head. These solenoids have microscopic metal screens wrapped around them to filter the oil before it enters the delicate phasing mechanisms. Here is the massive problem. If you listen to the dealership and stretch your oil change intervals out to 10,000 miles, the oil breaks down and forms a thick, abrasive black sludge. This sludge gets permanently packed into those tiny metal screens on the solenoids, completely choking off the oil pressure. The camshaft literally gets stuck in the advanced position when you come to a stoplight. The engine will shake violently. It will sound like an old diesel tractor, and it will throw a check engine light that perfectly mimics a bad MAF sensor or a massive vacuum leak. People spend entire weekends replacing spark plugs, ignition coils, and vacuum line, when the reality is that their variable valve timing solenoids are simply suffocating in dirty oil. I am about to explain how a very common, old-school cleaning habit will instantly destroy one of the most expensive sensors on your exhaust manifold. But before we get into that costly mistake, take 1 second to hit that subscribe button if you are learning something new for your garage today. Let us say your check engine light comes on, you plug in an OBD2 scanner, and it throws a code for a lean condition or a sluggish oxygen sensor. You grab your wrenches, slide under the car, and wrestle that sensor out of the exhaust pipe. You look at it, and the tip is completely caked in thick, black carbon soot. A lot of old-school mechanics will tell you to just grab a stiff wire brush or some rough sandpaper and scrub that carbon off to give the sensor a second life. That is the absolute fastest way to destroy the component permanently. The tip of an oxygen sensor or lambda sensor is not just a solid piece of metal. It is coated in an incredibly thin, highly sensitive layer of platinum and zirconium dioxide. This microscopic chemical coating is exactly what reacts with the exhaust gases to generate a voltage signal back to the computer. The second you drag a wire brush across that tip, you completely strip away the precious metals. The manufacturer treats these sensors like fragile glass because even a slight physical scratch renders them entirely useless. If the sensor is heavily carbon fouled, do not scrub it. You just have to bite the bullet and replace it. But physical abrasion is not the only way you can murder these sensors. The second massive mistake happens when people spray penetrating oil or silicone-based lubricants anywhere near the exhaust manifold to help loosen rusty bolts. These sprays release oily, silicone-rich vapors that settle onto the inner surfaces of the oxygen sensor. Once that chemical residue bakes into the sensor thimble from the extreme exhaust heat, it permanently poisons the element, blinding it to the oxygen levels in the exhaust pipe. The vapors can even travel downstream and coat the honeycomb inside your catalytic converter with a chemical glaze. Never use silicone sprays near your exhaust. If you are installing a brand new sensor, apply a tiny drop of high-temperature anti-seize compound only to the threads, making absolutely sure it stays far away from the sensing tip, and keep the electrical connectors completely bone dry. When these critical sensors fail or get coated in dirt, they often trick the engine computer into injecting way too much gasoline into the cylinders, creating what we call a rich fuel mixture. A rich mixture is a silent, catastrophic killer because the severe mechanical damage happens entirely out of sight, deep inside the engine block. The immediate symptom is usually thick, black smoke pouring out of the exhaust pipe, especially when you start the car or when you let your foot off the gas pedal. The exhaust fumes will smell intensely like raw, unburned gasoline, and you will notice your fuel economy absolutely tanking overnight. But the real tragedy is happening to your cylinder walls. In a healthy engine, your piston rings glide smoothly up and down the cylinder bore on a microscopic film of motor oil. That oil film is the only thing preventing the hard metal rings from gouging the metal cylinder walls. When your engine runs excessively rich for an extended period, that raw, liquid gasoline acts exactly like an industrial solvent. It physically washes the protective oil film right off the cylinder walls. Suddenly, you have raw metal scraping violently against raw metal at thousands of revolutions per minute. The cylinder walls become heavily scored, the piston rings wear out prematurely, and you lose critical engine compression. Worse yet, that raw fuel leaks past the damaged rings and mixes directly with the oil in your pan, severely diluting the viscosity of the lubricant that protects your crankshaft bearings. If you ignore a rich running condition for too long, a simple sensor replacement quickly morphs into a complete engine rebuild. This brings us to the final, incredibly destructive consequence of ignoring how your engine is running, and it involves your ignition coils and spark plugs. Modern engines use individual coil packs sitting directly on top of each spark plug to deliver a massive jolt of electricity, sometimes over 40,000 volts, to ignite the compressed fuel. Over time, the gap on your spark plugs physically widens as the metal electrodes wear down and the internal windings of the ignition coils begin to break down from the extreme underhood heat. When a coil gets weak or a plug gap gets too large, the spark gets blown out by the compression, resulting in a dead misfire. The cylinder completely fails to ignite the fuel. So where does all that raw, unburned gasoline go? It gets pushed straight out of the exhaust valve and travels directly into your catalytic converter. Your catalytic converter normally operates at a blistering 1,200 degrees Fahrenheit to burn off harmful emissions. When raw liquid gasoline hits that superheated ceramic honeycomb, it instantly ignites inside the exhaust pipe. The temperatures rapidly spike well over 2,500 degrees Fahrenheit, which physically melts the precious metals inside the converter into a solid, impenetrable block of glass. Your exhaust system is now completely choked off. The engine literally cannot exhale. You will step on the gas pedal, the car will refuse to rev past 2,000 revolutions per minute, and you will be looking at a massive $2,000 repair bill to replace the entire emission system. All because you ignored a slight engine hesitation or a flashing check engine light caused by a worn-out spark plug. Your modern vehicle is a highly complex symphony of electronics, sensors, and tight mechanical tolerances. Ignoring the warning signs, using the wrong cleaning chemicals, or stretching your maintenance intervals will always lead to catastrophic mechanical failure. I want to hear exactly what is going on in your own garage right now. Drop down into the comments section and tell me what OBD2 error codes you are currently fighting, what kind of weird hesitation your engine has on cold mornings, or how your fuel economy has been lately. Let us diagnose these issues together in the comments and figure out the best way to keep your vehicle on the road. If you learned a new diagnostic technique today and want to save yourself thousands of dollars in future repair bills, smash that subscribe button, leave a massive like on the video, and I will see you in the next one.